Good morning, everyone. Thank you for joining us today. We will start the webinar, so I hope everybody is comfortable. So we will make sure that everybody is on mute for the presentation. So please, if you join just now, just make sure you are on mute, so we have no other noise during the presentation. Thank you. So welcome everyone, as I was saying, to our webinar from Workstation to Driving Simulator from ViaGrade. So we will start now. So as first, I will introduce our two presenters. I am Mathieu Grob, a pre-sales manager at ViaGrade, and I will be your host today. And also, you can see we have David Ebank, is our senior technical manager at ViaGrade Limited in UK, and we'll perform our live demo today. So I will start with a brief introduction with our bridging the gap between testing and simulation, let's say, philosophy at ViaGrade. And then I will introduce what we call the ViaGrade complete workflow in a very short way. And then to expose you and to show you all the features, we will do mainly a live demo during this webinar. So I hope everything will be okay and no live demo effect. And we will start with showing you how to import a vehicle model into the real-time world, both from ADAMS or a KNC measurement. And then we will show you how we can perform testing and preparing all the model for the driving simulator up to, let's say, the motion queuing setup. We will finish the session by a Q&A session. So you can use the chat in the WebEx chat to ask your questions, and we will answer it at the end of the demo by listing the different questions and try to answer it as much as we can. Thank you. So let's go into the introduction. So first question, why a complete workflow? So as you know, real-time simulation and driving simulators are the new methods widely adopted by the automotive industry to develop innovative products in shorter time and with less cost. It's now become the new standard with simulation and driving simulators. So however, having those powerful tools, a robust and powerful workflow must be put in place in order to have a seamless transition from early concept design through real-time simulation to development and testing on the driving simulator. So ViaGrade is the only simulation company able to provide a complete and integrated workflow, leveraging the same software from your workstation concept design up to advanced driving simulator applications. So when we say that, it's a complete workflow from offline workstation simulation up to the driving simulator application. Yeah. So by doing that, ViaGrade is bridging the gap between offline, faster than real-time simulation, and online, powerful driving simulator capabilities, leading to better efficiency in your daily work. So on the right, you have an illustration that we will go in deeper detail with our ViaCar real-time vehicle model environments able to perform different disciplines and different applications up to all the driving simulator applications. So what do we mean by bridging the gap between testing and simulation? On the left, on this slide, you see the, let's say, classic V-cycle process that is used in most of the industry. With, on the left, your CA engineering part and virtual design part, when you design, simulate, and virtually test all your different concepts. And then on the right, you go to the manufacturing process, the testing, measurement, and finally the sign-off. And you have, let's say, more or less a clear separation between the virtual design and preparation and the testing part. At ViaGrade, what we want to achieve is to narrow and to bridge the gap earlier in the development development cycle here with the driving simulator, allowing to test in an early phase your virtual design and have your test drivers and CAE engineers collaborating at the same time here. So this is what we mean by bridging the gap between testing and simulation. How do we achieve that? We have developed one solution for every need by having a complete workflow that is our main focus today, from offline simulation through driving simulators up to in-vehicle testing. Then we have also developed a unique architecture for our driving simulator with unparalleled separation of chassis and body behavior. We will have a very brief overview of this. It's not the main topic today. And finally, we have a complete but yet open environment that is a turnkey solution to do all your workflow and simulation from offline to online, but that can be adjusted or interact with third-party software. So our main focus today in the VIA-grade complete solution will be the offline simulation and how we prepare to go from the simulation, offline simulation to the driving simulator. So of course, everyone starts with offline simulation. And with that, VIA-grade has developed a complete ecosystem to have a vehicle model with VIA-car real-time that we will introduce in a few minutes. And you can also have all your environment like controllers, different scenarios simulate, a driver, let's say a virtual driver, simulate sensors and events. All these are on the simulated side of the world. And of course, then you move to the driving simulator when you add some pieces of the real life inside, especially a real driver, but also you can have controllers and sensors. And so today we will explain how to move from this offline to online world in a very seamless way that we have developed. So to do that, we have developed a chain of software that allows this seamless transition. We start from the Adams car or virtual test rig or real test rig, let's say KNC rig import for vehicle characteristic. And we have developed what we call VIA-car real-time automatic building. It's part of our VIA automotive package to import those vehicle characteristics inside the real-time world. Then here we will show you how VIA-car real-time, our vehicle model, with our different modules, that is our VIA driver, our road modeling, our VIA tire interface, and our VIA animator visualization, allows to perform testing, simulation, and preparation for your vehicle and system, automotive system model. And then at the end, we will show you how to prepare your last transition to the simulator, that is the motion queuing, with our VIA motion queuing web tool and our VIA motion queuing offline. So thank you for your attention. Now I will let David show you a live demo of all these capabilities.
Okay, thank you, Matthew. Good morning, everybody. So I'd like to start this demonstration in the Adams car environment. A large number of our customers maintain their detailed vehicle model in the Adams car environment. So this makes it very easy to use that to transfer your model from Adams car into VIA-car real-time. And to do that, one of the tools we offer is a plugin for Adams car, which gives access to the VIA-grade utilities that will exercise the Adams car model and create VIA-car real-time model. So for this, we can choose to do either a suspension assembly or a suspension and steering assembly, or we can do a complete full vehicle model. So in this case, we're going to export a complete vehicle model. So in the dialog box for this, we have a few options. So we can set the export parameters, and this covers things like setting the bump and rebound travel for the suspension, so that we exercise the suspension throughout its complete range of travel. We can choose to enable compliances, and we can specify the load limits for those lateral, longitudinal, and aligning torque compliances. For the purposes of this demonstration, I'm not going to do compliances, purely for time constraints. To give you an idea, doing a kinematic export takes approximately 2 minutes. If I enable the compliances, that increases up to maybe 5 minutes, to give you some idea. Now, this vehicle model is a fairly typical small town car, McPherson strut front suspension, torsion beam rear suspension, in this case including a flex body. So some of the other setups in here, we can decide, is the vehicle, does it need to run a dependent suspension analysis? If so, how many iterations of that do we want to run? Do we want to run the compliance analysis at a number of different roll angles, as well as at different parallel wheel travel heights? We can specify the delta jumps for the roll simulations. We can also specify the parameters for identifying the longitudinal dynamic degree of freedom of the wheel. That might be useful if you've got a suspension that includes a hydro bushing with some frequency-dependent characteristics. Also in here, we can specify what range we want to test the steering system at, how many different parallel wheel travel heights we wish to test the steering system, and whether we want to do a detailed analysis of the steering rack system itself. That's useful if we wish to do a more advanced steering modeling once we're in the VICAR real-time environment. Okay, so once we've set those up, we specify what our model name is going to be, which database we want to put the data in, we choose to run the solver. So in this case, I'll launch that to run, and I'll explain the different steps in the process. So the first step it does is generate a front suspension and steering assembly. Now in this case, it's created that directly from the full vehicle assembly. So we're using the standard Adams car suspension test rig. So if your model is compatible with that, it should also be compatible with doing the export. We're going to run a series of different simulations here, comprising tests such as a parallel wheel travel, with and without gravity. We'll do an opposite wheel travel. We'll do normally a series of lateral longitudinal compliance tests. We'll look at the anti-roll bar characteristics. Obviously for the front axle, we'll also do a series of steering sweeps, and we'll look in depth at the steering system characteristics. And through that, what I mean is we'll look at the relationship from the hand wheel to the rack displacement, looking at things like column phasing in there. We can identify any steering column isolators that may be present in the system. And then we also look at the relationship between the road wheel steer angle and the steering rack displacement, as well as the relationship between the total kingpin moment and steering rack force. So it's done the front suspension, and we've now opened up a assembly for the rear suspension, and you can see the flex body used for the cross beam. So in this case, we'll run through the same set of tests, obviously not including the steering system in this case, but you can include rear axle steering as well, if that is a feature of your model. So again, it's running through the kinematic tests first, followed by the compliance tests, although we're not running those for this demonstration. And then when the rear suspension's finished, it will then go back to the full vehicle, and it will extract the geometry, the full vehicle mass and inertia characteristics, the wheel and tyre subsystems. If the powertrain exists as a separate lumped mass in the Adams car model on bushes, then we can also extract that to VICAR real-time, giving you a more representative model. And then, in this case, the simulation and the export has finished. Now, ordinarily, we could go straight into VICAR real-time now, open up the model and start running some tests. But whilst we're in the Adams car environment, I want to look at another tool that exists in here to allow us to do some automated model validation testing. Okay, so we'll close those. Now we'll open up the next test. So what this allows us to do is run a series of suspension tests and full vehicle tests on both the Adams car model and the already created VICAR real-time model. The same tests in both environments, and then it will create an HTML report which includes an overlay of all of the results for those. And we can choose, I'm going to say, front suspension, in which case we'll look at the basic the kinematic, parallel wheel travel, opposite wheel travel, and if relevant, we'll look at the compliant behavior as well. For the full vehicle tests, for the lateral, it would do a step steer and a ramp steer test. We'll look at longitudinal tests for acceleration and braking. We'll run both models over a swept sinusoidal vertical road input to look at the vertical dynamics for the two vehicle models. And for the combined test, we'll look at a brake and turn maneuver. And then obviously it will go on to produce the HTML report. I'm not going to run the simulations live during this because it takes a few moments. So here's a HTML report I created for this model earlier. So the header information in here is telling us which validation tasks have been completed. We then get a comparison of the Adams car versus the VI car real-time models in its design condition, and again a report in the dynamic test condition. As we start looking through the plots, we've got the front suspension and rear suspension tests. So in this case, we're looking at parallel wheel travel. In this case, it's the bump steer characteristic. And as you can see, the correlation is pretty good. You're hard pressed to tell the curves apart. For opposite wheel travel, again, the correlation is pretty good. You might notice a small variation between the curves, but then when you look at the scaling, actually the differences are insignificant at this stage. For compliances, again, the correlation is extremely good. Again, on the rear suspension, remembering this has a twist beam in the Adams car model. Again, very good correlation for parallel and opposite wheel travel, and also for the compliances. When we look at the steering sweep, again, very good correlation between the two models. For full vehicle maneuvers, if we look at the step steer, there is some small deviation between the two. Now, ordinarily, I'd like to see this a little bit better, but it can be explained by the fact that in the Adams car model, we have a full power steering assistance system. And in the VI car real-time model that's been created in this case, we've only got a very basic representation of steering assist. So there are some differences there. And if we expand the VI car real-time model to include the advanced steering model, I would expect these differences to disappear. So that's a step steer, the impulse steer, brake in turn, and then finally the swept sinusoidal input on a road looking at vertical dynamics. Again, showing extremely good correlation between the two, especially considering the Adams car model has several hundred degrees of freedom, but the VI car real-time model in this case has 18 degrees of freedom. So I think that correlation is very good. Okay, so that report is generated automatically for us. So once we've gone through that process, we've created the VI car real-time model, we've looked at the auto validation. It's then time to switch to the VI car real-time interface to look at, we'll come back to the vehicle model itself in a moment. What I want to do first is look at an alternative way of creating the VI car real-time model. So this happens quite often in automotive companies. You have all of the information for your own vehicle model, but often, especially if you're looking at moving to the driving simulator, it's all very well driving one vehicle model, but it's nice to have a reference model. So you might also wish to include your benchmark vehicles in there as well. And normally you don't have access to all of the design information for your benchmark vehicles, but you can put them through kinematics and compliance rig testing. And that's a very good starting point for creating a VI car real-time model for your benchmark vehicles. So one of the utilities we have available is the KNC Wizard. Now let me just open up a input file for that. So in the KNC interface, this is allowing us to identify some full vehicle information, so things like wheelbase, track, center of gravity height, vehicle mass, and so on. Not strictly necessary, but is useful because what we get is a complete and valid vehicle model at the end of this process. Of course, all of this information can be updated once we have the model in VICAR real time. So we're also adding in information for suspension and wheels. The useful information here is if you have access to the damper motion ratio. Typically, a KNC test rig does not compute the motion ratio for either springs or dampers. We can add in basic powertrain data, brake system data, and steering data. Once we've got the basic vehicle parameters imported, we can then start mapping the internal channel names that VICAR real-time uses with the corresponding name in the KNC test data. So in this case, we're looking at identifying, in this particular signal is front left wheel travel. Now I happen to know that in the test data, that's LFZ0. We can set the scale factor, so we could look at addressing differences in units or sign convention, and we can apply offset if necessary for the data in here. So we can map all of the channels that will be used for doing that import. Again, once we've done that, we can then start defining which different load cases we're going to run. So these are separated into kinematics, roll, compliance, steering systems. So for each of these, there isn't a precisely defined list of load cases that you must have, but obviously the more sets of data that you can apply to the model, the more complete VICAR real-time model will be. The minimum data we need is a parallel wheel travel and opposite wheel travel for both front and rear suspensions. In this case, we've also got test data for single wheel travel tests, in this case individually for the front left, rear right, front right, and rear left wheels. Accordingly, we're picking out the corresponding data files for those. Now, if I just jump out to a text file, let's show the folder with all of those data files in. So these are exactly the files that have come from the testing company. In this case, I think it was a MTS test rig, but we don't care whether it's an MTS test rig, an Anthony Best, an in-house test rig. As long as you can exercise the vehicle model in the appropriate way, we can map the data for it. And as you can see in this particular test data file, we've got lots of header information that we can ignore before we get to the main data. So moving on from kinematics, we're defining the roll load cases. Now, for things like roll, it's often useful to look at the roll characteristics at a number of different parallel wheel travel heights. This gives us a more complete model in VICAR real time. For example, if you want to change your vehicle load condition, obviously that might give you a different ride height for the vehicle, which could give you slightly different roll characteristics or compliance characteristics, steering characteristics. So what you'll see in these load cases is additional load cases for 40 millimeters into bump, normal ride height, and 40 millimeters into rebound for all of the compliances, the steering, and for the roll conditions. Now that gives us quite a complete model in VICAR real time. If that data is not available, so typically in a KNC test, the compliances are only calculated at a single ride height. That doesn't really matter for VICAR real time. We can create a model from that. But obviously, if you then want to change your ride height, you might not be recreating exactly what would happen on the real vehicle. We can't make up data from the thing. Okay, so you'll see here there's lots of data for compliances. Some of these will be parallel inputs, some of them will be opposing, some will be single wheel inputs. All of that data will be used to compute the suspension models in VICAR real time. Likewise for the steering, in this case we've done steering sweeps at normal ride height, plus 40 millimeters and negative 40 millimeters in parallel wheel travel. Okay, so once we've assigned the plots, we can then fit the data, and that will then give us after a few seconds, a comparison for the raw data versus the fitted data. And I could go on from here and export the vehicle model from the wizard into VRCar Real-Time. One of the options we have is to create an HTML report from this. And I'm now going to jump to one we created earlier, just to give you an idea of what will be included in there. So in this case, we can see the fitting report. We have a summary at the start that shows the different classes of load case, the different types of the individual load cases, what role they are, is it a front axle or rear axle, and what the side of the vehicle is, as well as the path to the individual data files. And then as we start to get to the validation plots, we can see in this case, the KNC test data is shown in red. So that's our raw data. And the blue curve shows our fitted data along with the number of data points that have been chosen. So even when we've got considerable hysteresis in the raw KNC test data, the fitted result is actually a pretty good fit to those. So we could go through all of these. I think you get the picture. That's quite a comprehensive fitting report, and that should give us good confidence that the VRCar Real-Time model we create is a good representation of the raw KNC data. Okay, so moving on from importing models, once we have the models inside VRCar Real-Time, we'll see if we're familiar with Adam's car, but actually the model is separated into a similar set of subsystems. So we have front suspension, rear suspension, steering, a body subsystem, front wheels and tyres, rear wheels and tyres, brakes, powertrain, and possibly some auxiliary options as well. And if we look in the front suspension, we can see, in contrast to Adam's car, which is a very graphical environment, in VRCar Real-Time, we're very much more text and data driven. So we see lots of curves that show our data points. So in this case, we're looking at the left x coordinate of the wheel center and how that changes relative to the parallel wheel travel height. The number of curves in here are showing how that varies with the opposite wheel vertical travel, or if you like, different roll cases. So we also have orientations. So again, here we're looking at side view angle change versus parallel wheel travel height, again with different opposite wheel travels. For compliances, we separate these into direct compliances and opposite wheel compliances. And by that I mean you put an input into your left wheel, potentially, depending on the suspension architecture, you may get a residual change to the characteristic on the right suspension as well. So in here, we've separated the compliance loads out into longitudinal force braking, longitudinal force traction, lateral force, aligning moment, and optionally a vertical force component as well. And again, we can look in these tables and we can see we've got toe angle versus longitudinal force at different ride heights. Likewise, springs, dampers, bump and rebound stops, anti-roll bars are all driven through the curves created either from the Adam's car model or from the KNC import. Okay, so moving on from the model itself, we can now look at the test mode. And within VRCar Real-Time, we have a whole series of library test events that are predefined for you. And these cover maneuvers such as braking in a turn, constant radius cornering. We've got some course events which we'll touch on shortly with some demonstrations. Open loop steering, so we've got predefined impulse steer, ramp steer, sign steer, step steer, swept steer. Stability tests, so things like fish hook, J-turn, sign with dwell. We've got straight line acceleration and braking. We can offer various different safety events, so sort of a lateral curve trip rollover test, various different misuse tests, and then we can connect to sort of external test rigs as well. So I'm not going to concentrate too much on the basic maneuvers in here. Instead, I'm going to look specifically at two of the more complicated events that we can run. Right. So the first event we're going to look at now is a maximum performance. And by that, we mean really a dynamic lap time simulation, where we're going to calculate the maximum speed that the vehicle can go around either an open course or a closed circuit without exceeding predefined distance from our target driver line. So in this case, we're going to use a Calabogie test track. We're going to run a flying lap. We're also going to create the input files that we might use if we were going to pass this vehicle model on to use on the driving simulator. Now, the max performance test is quite a good way to exercise our vehicle model, to test it for robustness in the same sort of way that we might need to if we're passing the model onto the driving simulator. Obviously, human drivers can sometimes be less predictable than robot drivers, so it's useful to explore the limits of vehicle behavior. Okay, so we will automatically create that. So I'm going to run this as a live simulation. So that will take it a few seconds to get going. Then we should see that come on full screen. So this takes a very iterative approach to finding the maximum performance. And if I just pull up the window there. So we've got a predefined target driver line that we're going to ask our driver model to follow. And if it senses that the vehicle model is unable to match the target speed profile calculated by a quasi-static model, then it will recognize if we're running wide of our target line, if we've got wheels locking under braking, or maybe spinning under acceleration, and it will go back and modify the friction in the road model for the quasi-static model only. Then regenerates a new target speed profile for our dynamic model, attempts to run that, and as you can see here, we've got quite a iterative process. So if I just look into the speed plot a little bit more, you'll see there's lots of variations in here. If I zoom in a bit, where we've got multiple repeats of the same segment of track. And in this case, what's happening is the higher speed was not attainable by the dynamic vehicle model. It might have understeered wide, there might be excessive oversteer, it could have been locking a wheel under braking, and so on. So as it runs more iterations for these segments of track, you'll find that the speed through that corner alone gets a little bit slower until the dynamic model is able to successfully negotiate that corner. So that's now finished running the lap. And if I just stop there and reload the results and just jump back to our table, what we get in here in our sort of information window is a summary at the end that shows the different distance markers around the lap. So we call these different segments, and what our final scaling factors were for the quasi-static model under acceleration, braking, and cornering, and how many iterations each of those segments took. So some of these have clearly taken a little bit more effort than others, but the end result is a very reliable maximum performance lap. And if I play here, you should be able to see that in action. So the interface we've got open now is our VI animator interface. It's not the same as we would use on our driving simulators, but it's more of an engineering interface where we can create and define our own performance plots that we might be interested in. We can do curve calculations in here and generally use it as a tool to interrogate the response of our vehicle model. Okay, I'm not going to run that through to the end. Instead, let's jump now through to our next event that I want to look at. Now, both the max performance and the press maneuvers are quite unique amongst vehicle dynamics tools in terms of the capability. So the press maneuvers is really going to look at things like the ISO double lane change, and within there we look at the correct cone spacing for that. We've got the double lane change consumer report, obstacle avoidance, 3 different varieties of slalom test with different cone spacings, and a custom option which allows you to adjust the cone spacing to your own company specifications. We do detect contact between the vehicle body and the cones used during the test, and we can use the vehicle graphics for that. So in this case, let me just run another live animation. Again, this is an iterative approach. So you can see the cone separation there. Now, initially, the first few attempts, the driver model is attempting to find a driver line that is suitable to successfully pass through the cones. And as you can see, that iterative process progressing, you'll see we get a little bit further each time. Hopefully we should get through very soon. Yeah, that was its first successful iteration. Now it's going to start ramping up the test speed until such time as it's no longer able to maintain that existing hand wheel input to get through the test. And in that case, it will go back and then start to redefine the target driver line to get through the cones. So that will run out of performance very shortly. And we can set additional refinements here, which would, once it gets to the limit of performance, will go back to its last successful speed and take a smaller speed increment. So that's quite a powerful utility, and we've come to the conclusion there. And again, if we look in the output plot from it, we can see in this case it went through at an average of sort of 84 kilometers an hour. And we could look at how the vehicle setup changes might affect the performance through the lane change. Okay, so that brings me on to one of the options we have for outputs from here is a custom report. Now, in this case, we'll go back to the maximum performance, as well as having the VI animator to view the results in. We can define our own set of numerical results, metrics, graphical plots, and curves that we might want to have created automatically into an HTML file. As you can see here, we've got various standard outputs from the model. We have a longitudinal velocity map around the circuit, and then a series of time history plots as well, right the way down to a GG diagram. So all of these plots can be customized. The code behind those is all Python-based. Again, that can be quite useful for creating quick reports on your different simulations. So once we've got our vehicle model, we've got our events defined, and we're looking at that. Often what we want to look at is what does the effect of making design changes to our vehicle have on performance. And for that, we can look at investigation mode. So in investigation mode, we can pick, in this case, I've got a sinusoidal steering test, but we can use any of our existing test events or multiple test events. We don't have to have just one here. And then we can decide on a number of different design parameters in the vehicle model to include as factors in the model. Now, in this case, I've chosen the front and rear anti-roll bar scaling factors. And then we can look at one or multiple responses that we're interested in. In this case, I'm looking at the absolute value of yaw velocity as an output from the test. So for the different factors, we can either choose absolute values, relative values. So in this case, I'm scaling the anti-roll bar stiffness. So I've gone for relative, and it's scaling them between 0.5 and 1.5 of their nominal value. And you can specify then how many different levels do you want to look at for each of those. And we can choose whether we want continuous or discrete parameters. Finally, when we set that up, we decide, do we want to run a full factorial test? That can generate quite a lot of simulations. So in this case, I'm looking at 5 levels with 2 factors which gives us the full factorial, obviously 25 simulations to run. We could look at two-level factorial, where we're doing sort of response screening, or we can indeed define our own custom table of simulations to run. Once that runs through, so that can run automatically, we can look at the results. So firstly, it's showing the different iterations it ran and the values used for each of our factors. Back this one. Apologies, the wrong one. So if I look at the one that's already got the results in, so we're looking at the individual iterations, the factor values used. Was that particular iteration successful? Or maybe one of them put the vehicle model in a case where it can't run, and what the response value is. In addition to that, we also get a parallel plot, which allows us to then drill in and filter down through results, which can be quite useful to understand the influence of different factors on our response metrics. Okay, so that can be quite useful, particularly if we're going on to the driving simulator. Obviously, time spent in the driving simulator is quite valuable. So we might want to have a very good understanding of what changes we can make to our vehicle model and what we would expect those changes to have on our vehicle performance. And it's always useful to understand that before we go to a driving simulator session. So now I'd like to hand back over to Matthew.
Okay, thank you very much, David, for your demonstration. So we have now, sorry, I just hide this, okay. So we have now been through all these different steps that I explained you at the beginning, so the VI automotive plus VI car real-time process. And now, let's imagine you have performed these different tests and you want to go on the driving simulator. So first thing you have to know is that the software and the solvers are consistent from your offline to our online simulation. So it means that all the simulations and the files and the vehicle models you have created so far can be used as it is on the driving simulator. You have no special version of the software, no special version of the software. It's exactly the same solver, the same software, the same real-time capabilities. So the only thing you have to do is to be sure that when you will go on the VI on the motion queuing on the platform, your vehicle or maneuver will be okay with the motion queuing and with the platform. So for that, we have a very simple way to help at the beginning. If you go on our website, so this is the ViaGrade website, you can create a login, so you can register for free and create a login and access to our reserved area. So I will log in right now and show you. And here, on our reserved area, you have different things like our software download and so on. But you have also our VI motion queuing web tool. So the purpose of this tool is to give you access to statistical validated motion queuing files. So you don't have to, by yourself, create from scratch a motion queuing file, and you can load it from a validated database. So how it works? Basically, as David showed, we have different kind of tracks and vehicles already loaded in the VIA car real-time database, but you can have your own. So here is a web interface of all our motion queuing parameters. And so what you have to do is to say, okay, I want to select a type of car. So for example, with David, the demo, we have used a sedan passenger car and a type of track. So we have done here on a racetrack that is Calabogie, that is you have a little bit of hills, some hills on it. So let's say you want to drive on a hilly track. And here, as you have seen, it has already created and loaded all the motion queuing parameters. The only thing you are missing is the axis of rotation, because it depends on your car. So for this, I have already prepared for the sedan car my axis of rotation. So if I load my my motion queuing file, you can load your own motion queuing file and compare it to the one we have online, and to see if you are far or not from our, let's say, standard motion queuing parameters. So here you see that I use exactly the motion queuing file from the website, but I have just completed the axis of rotation. So now, if we move to the motion queuing, I will launch DriveSim. That is our software, both on Windows and Linux, that is used to launch simulation for driving simulators. So it's kind of the hub. Then will let's say coordinate actions between the ViaCar real-time software and solver and the DriveSim interface, that is our graphics for the road graphics, all the action feedback and body feedback and force feedback from the motion queuing and so on. And you have a motion queuing tab where you can test your motion queuing. So what you need to have for this is a result file. So this is the result file David has just computed with max performance. So he has done an optimization around Calabogie racetrack, a result file. So I will load it. It's on car max performance race file. I load also my motion queuing file that I have, and I just choose a CSV file to store the results. So I want to compute the kinematics for the DIM 150, that is our 1.5 meters workspace dynamic simulator. And I want to show you in VI Animator the post-processing to show you how it works. And I just click Run Test, and now DriveSim will compute the motion queuing animation based on the max performance event. So basically, we will replay with a virtual motion queuing platform the maneuver computed in max performance. So all the racetrack lap on the Calabogie racetrack will be now played with the motion queuing. So you will see in a few seconds how it goes, and so it allows you to check that the motion queuing is good for this maneuver. And then, of course, if you want to change the motion queuing, you can do this test many times to check that it's still working, that you are not out of the boundaries of the platform, and so on. So now VI Animator is loading the results. So as you can see now, we see our little driving simulator here. I will zoom in a little bit. Yes, and I will start the animation. So I hope you can see it moving. So here you are testing your Calabogie lap on our VI motion queuing offline algorithm. So you can see you have a visual of what is doing the platform. So you can see exactly how it's moving, how the different actuators are going, and so on. And also on the right, you have a lot of plots to check that your animation is going well. So you can, for example, plot your chassis acceleration lateral versus your queuing acceleration lateral. Our platform can go up to 1.5 G maximum, but here is a scaled motion queuing because, of course, you have a lot of, it's a racetrack, it's a demanding racetrack, so you have to be aware that if you go full motion, you don't have time to come back to the center of the platform. And for example, here you can see the platform position and if you are still in the limit of the workspace. So you have different already prepared post-treatments, and here are the driver demands, to analyze your motion queuing. And also we have generated a CSV file with all the input outputs, and so you can go in deeper analysis if you need. So now we have everything. We have our vehicle model that is prepared. We have our the motion queuing that is prepared. So the last thing we need is to go on the driving simulator. And for that, thanks to ViaCar Real-Time, you just have to load your vehicle model and to create a VI DriveSim event that will create a file here, that I have here, a little XML file that you can just copy-paste on the driving simulator and launch the simulation. Basically, it's a file where all the information of what you want to do is stored. So you will use the same vehicle model, the same solver, the same track model, the same tire model, everything will be the same, and you will be able to drive it just with one click. So we have finished the live demo. So as a conclusion, as you have seen, just a small illustration of our driving simulator that then you can use with exactly all the files you have created. So it's our simulation platform called the Driver in Motion, the DIM, that has a double, let's say, a hybrid architecture between a tripod that for tire-to-road contact and, let's say, low-frequency vehicle dynamics maneuver, and an hexapod for high frequency and high dynamics maneuvers. So it allows to separate low and high frequency and have also redundancy of movements to allow you to use the maximum of the workspace available. So what we have seen today is that you have a complete workflow of tools, including VI motion queuing that we have just seen, via career time that we have been through with David, using the multi-body interface that is with Adam's car and we call VI automotive. And we have also our graphical environments that we didn't demonstrate today because it's for the driving simulator to use on all the graphical environments properly modeled. And then we can use all this workflow seamlessly on Workstation or to go on any of the driving simulator line that we have at ViaGrade. And we have also all the open environment interface that we didn't detail today, but could be a discussion for another webinar, with, for example, the tire interface with the compatibility with all tire models on the market, all the graphical interface for traffic environment, for example, of course, a MATLAB interface for custom components, and an HIL interface. So as a conclusion, we have showed you that via career time allows to have one single reliable and consistent vehicle model and environment from your workstation up to the driving simulator. And we have been able to show that we can bridge the gap between testing and simulation by providing interface from your CAE environment or testing world like the KNC to the ViaGrade real-time ecosystem in order to accelerate design and develop new automotive solutions. So thank you for your attention. Before moving to the questions, if you have some, if you are interested in what you have seen in more detail, you can visit our website that I just showed you. We have an automotive web page describing all the different products we showed you today. You can register for free and get access to the motion queuing web tool and all related publications from our conferences, for example. You can go on our YouTube channel, on our LinkedIn page, or you can contact me directly if you have any more questions. Thank you very much for your attention.